November 24, 1944. Saipan, Mariana Islands. The pre-dawn darkness erupts with the roar of 18 cylinders as B-29 Superfortress, serial number 42-24592, piloted by Major Robert Morgan, begins its takeoff roll. The massive bomber, weighing 120,000 pounds fully loaded, accelerates down the 8,500-foot runway at Isley Field. In the flight engineer's position, Technical Sergeant Henry Carlson monitors 4 critical instruments: turbo-supercharger RPM gauges for each of the 4 Wright R-3350 engines. As Morgan advances the throttles, Carlson carefully adjusts the turbo controls, watching exhaust gas temperatures and manifold pressure climb to optimal levels. The B-29 rotates at 135 miles per hour, climbing into the tropical night. Their target? The Nakajima Aircraft Company factory in Musashino, on the outskirts of Tokyo, 1,500 miles to the north. This mission would have been impossible just 3 years earlier. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The distance from Saipan to Tokyo and back 3,000 miles exceeded the combat radius of every bomber in existence before 1944. The key to this unprecedented range wasn't just the B-29's streamlined design or massive fuel capacity. It was 4 turbo-superchargers, one mounted on each engine, that could maintain sea-level power output at 30,000 feet while consuming fuel with an efficiency that seemed to defy physics. These devices, spinning at 25,000 revolutions per minute and handling exhaust gases at 1,600 degrees Fahrenheit, represented 20 years of American engineering innovation. They would enable the strategic bombing campaign that brought Japan to its knees, flying missions of such distance and altitude that Japanese interceptors could barely reach the bombers, and anti-aircraft guns couldn't touch them. The story of how turbo-superchargers extended the B-29's range by 2,000 miles is more than a tale of mechanical ingenuity. It's the story of how American engineering supremacy created weapons systems that rendered enemy defenses obsolete, conducting warfare from altitudes and distances that seemed impossible, and ultimately delivering atomic weapons that ended the Pacific War. To understand the revolutionary impact of turbo-superchargers, one must first grasp the fundamental problem they solved: the devastating loss of engine power at high altitude. This wasn't merely an inconvenience, it represented a physical barrier that limited bomber effectiveness and made aircraft vulnerable to enemy fighters and anti-aircraft fire. At sea level, atmospheric pressure is 14.7 pounds per square inch, and air contains approximately 21% oxygen. Aircraft engines, like all internal combustion engines, require oxygen to burn fuel. The chemical reaction is straightforward. Fuel plus oxygen produces power, carbon dioxide, and water vapor. The amount of power an engine produces is directly proportional to the mass of air it can ingest and the fuel it can burn. As altitude increases, air pressure decreases according to a predictable mathematical relationship. At 10,000 feet, atmospheric pressure drops to 10.1 pounds per square inches, a 31% reduction. At 20,000 feet, it's 6.4 pounds per square inches, a 56% reduction. At 30,000 feet, the B-29's optimal bombing altitude pressure is only 4.3 pounds per square inches, a catastrophic 71% reduction from sea level. For an unsupercharged engine, this translates directly to power loss. A 2,000 horsepower engine at sea level produces only 1,380 horsepower at 10,000 feet, 880 horsepower at 20,000 feet, and a mere 580 horsepower at 30,000 feet. This 71% power loss made high-altitude operations virtually impossible for early bombers. The B-17 Flying Fortress, America's primary heavy bomber in the early war years, demonstrated these limitations perfectly. Powered by 4 Wright R-820 Cyclone engines producing 1,200 horsepower each at sea level, The B-17E model could cruise at 210 miles per hour at 25,000 feet, but its engines struggled to maintain even 400 horsepower each at that altitude. The bomber's service ceiling, the maximum altitude at which it could maintain level flight, was 35,000 feet theoretically, but practically it operated between 20,000 and 27,000 feet. At these altitudes, B-17 seconds remained vulnerable to German and Japanese fighters, which could climb higher and had better performance characteristics at altitude. Anti-aircraft fire, particularly the German 88mm flak guns with ceiling capabilities exceeding 30,000 feet, extracted devastating tolls. During the Schweinfurt raids of August and October 1943, the 8th Air Force lost 120 B-17 seconds, primarily due to operating within the engagement envelope of German defences. The range implications were equally severe. An aircraft's range depends on fuel capacity divided by fuel consumption rate. Fuel consumption increases dramatically as engines struggle to produce power at altitude. The B-17's combat radius of approximately 1,000 miles limited strategic options. From England, B-17 seconds could reach Western Germany but not Berlin until escort fighters became available. From Pacific bases, they couldn't threaten Japan's home islands. Japanese defenses, in 1943, reflected confidence in altitude limitations. The Nakajima Ki-44 Tojo fighter, optimized for high-altitude interception, had a service ceiling of 36,000 feet and could reach 30,000 feet in under 15 minutes. The Kawasaki Ki-61 Tony could climb to 35,000 feet. Anti-aircraft batteries ringing Japanese industrial centers could engage targets up to 32,000 feet. Japanese military planners believed their homeland invulnerable to strategic bombing because no American bomber base existed within range of Japan. The solution to the altitude problem required forcing more air into engines supercharging. Mechanical superchargers, driven directly by the engine crankshaft through gears, had existed since the 1920 seconds. These devices used a compressor to increase air pressure before it entered the engine, partially compensating for altitude losses. However, mechanical superchargers consumed substantial engine power to operate, typically 100 to 150 horsepower, reducing overall efficiency. The breakthrough came from an entirely different approach, using exhaust energy to drive the compressor. This system, called a turbo-supercharger or turbo-supercharger, recovered energy that would otherwise be wasted as heat, converting it into compressed air without parasitic power loss from the crankshaft. The efficiency gains were revolutionary, but the engineering challenges were immense. The story of turbo-supercharger development begins not with the military, but with an engineer's determination to solve a fundamental thermodynamic problem. Dr. Sanford Alexander Moss, born in 1,872 inches San Francisco, joined General Electric's steam turbine department in 1903 after earning his doctorate from Cornell University. His expertise in thermodynamics and gas flow would prove crucial to American air power. Moss's breakthrough came in 1918 during World War I. While the war ended before his device saw combat, the Army Air Service recognized its potential. On September 25, 1918, at Pikes Peak in Colorado, altitude 14,109 feet, Moss conducted a demonstration that would change aviation history. A Liberty L-12 engine, normally producing 350 horsepower at sea level, but barely 230 horsepower at Pikes Peak altitude, was fitted with Moss's experimental turbo-supercharger. The results stunned observers. The turbocharged Liberty engine produced 356 horsepower at 14,109 feet, actually slightly more than at sea level, due to the cooler air temperature. More remarkably, when adjusted for the colder air density, the engine maintained full sea-level power output. The Army Air Service immediately recognized the strategic implications. Bombers could operate at altitudes unreachable by enemy fighters, above anti-aircraft fire, with full engine power. However, translating laboratory success to operational aircraft required 2 decades of intensive development. The challenges were formidable. Materials capable of withstanding 1,600 Fahrenheit exhaust gases while spinning at 25,000 revolutions per minute, control systems that could regulate boost pressure across varying altitudes and power settings, ducting that could channel superheated exhaust gases without melting or catching fire, and bearings that could survive extreme temperatures and centrifugal forces. General Electric's Supercharger division in Lynn, Massachusetts, became the center of American turbo-supercharger development. By 1938, when war clouds gathered over Europe, GE had refined the basic design into a practical device. The Type B-2 turbo-supercharger, developed for the Boeing B-17, demonstrated the system's potential. This unit could maintain sea-level manifold pressure up to 25,000 feet, giving the B-17C model released in 1940 significantly improved high-altitude performance over earlier variants. The turbo-supercharger's operating principle was elegant in theory, but demanding in execution. Exhaust gases from the engine, instead of venting directly overboard, were channeled through ducting to a turbine wheel. This wheel, typically 9 to 11 inches in diameter, was connected via a shaft to a centrifugal compressor wheel on the opposite end. The turbine extracted energy from the hot, high-velocity exhaust gases, spinning up to 25,000 revolutions per minute. The compressor wheel, spinning at the same speed, drew ambient air and compressed it through centrifugal force. Radial vanes on the compressor wheel accelerated air outward, where a diffuser section converted velocity into pressure. This compressed air, now at higher pressure than ambient altitude, was then cooled in an intercooler before entering the engine's conventional mechanically driven supercharger for final compression. The genius of the system lay in energy recovery. Exhaust gases that would normally be wasted heat were instead converted into compressed air, essentially providing free supercharging without parasitic power loss from the engine crankshaft. The efficiency gains were substantial. At 25,000 feet, a turbocharged engine could produce the same power as at sea level, while consuming only marginally more fuel than an equivalent unsupercharged engine at sea level. Control systems represented critical challenges. Too much boost pressure would cause detonation, destroying the engine in seconds. Too little boost meant inadequate power at altitude. The wastegate, a valve that bypassed exhaust gases around the turbine, provided variable control. At low altitude, where full turbo boost wasn't needed, the wastegate opened wide, allowing most exhaust to bypass the turbine. As altitude increased, the wastegate gradually closed, directing more exhaust through the turbine to maintain manifold pressure. Pilots and flight engineers controlled the wastegate manually or through automatic regulators, constantly adjusting to maintain optimal boost pressure. This required skill and vigilance. An inexperienced operator could overboost the engine during rapid altitude changes, causing catastrophic failure. Training emphasized smooth, gradual adjustments and constant monitoring of manifold pressure, exhaust gas temperature, and turbo-supercharger RPM. By 1940, American aircraft manufacturers had embraced turbo-superchargers for high-altitude bombers. The Republic P-47 Thunderbolt fighter, powered by a Pratt & Whitney R-2800 double Wasp engine with a General Electric CH-5 turbo-supercharger, could maintain combat power above 40,000 feet. The consolidated B-24 Liberator, using turbocharged Pratt & Whitney R-1830 twin Wasp engines, achieved operational ceilings exceeding 30,000 feet with bomb loads. However, the B-29 Superfortress would push turbo-supercharger technology to its absolute limits, requiring devices that could function reliably for 15-hour missions over oceans, endure combat, damage, and provide unprecedented performance margins. The Boeing B-29 Superfortress represented the most technologically advanced and expensive weapons program of World War II after the Manhattan Project. Development costs exceeded $3 billion more than the atomic bomb program and pushed American aeronautical engineering to its limits. At the heart of this revolutionary bomber was a propulsion system that would enable missions previously considered impossible. Specification requirements issued by the Army Air Corps in 1940 were daunting. Maximum speed 400 miles per hour, range 5,333 miles, Bomb load 2,000 pounds at maximum range or 20,000 pounds short range, service ceiling 40,000 feet, defensive armament sufficient to fight without fighter escort. These requirements exceeded any existing bomber's capabilities by factors of 2 to 3. Boeing's design team under Chief Engineer Edward Curtis Wells understood that meeting these specifications required revolutionary approaches. The B-29 would be the largest bomber ever built, with wingspan of 141 feet, length of 99 feet, and maximum takeoff weight approaching 140,000 pounds. Powering this massive aircraft required engines producing unprecedented horsepower at high altitude. Wright Aeronautical Corporation received the contract to develop the engine, the R-3350 duplex Cyclone. This 18-cylinder, twin-row radial engine displaced 3,350 cubic inches and was designed to produce 2,200 horsepower at takeoff, more than any previous production aircraft engine. But horsepower at sea level was insufficient. The engine needed to maintain power at 30,000 feet. This required turbo-superchargers of unprecedented capability. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. General Electric developed the Type B-11 turbo-supercharger specifically for the B-29. This unit represented the pinnacle of 1,940 seconds supercharger technology. The turbine wheel, 10.5 inches in diameter, was machined from Inconel, a nickel-chromium superalloy capable of maintaining strength at extreme temperatures. The compressor wheel, also 10.5 inches, was precision-balanced to minimize vibration at 25,000 revolutions per minute. The B-11 could maintain 46 inches of manifold pressure, significantly above sea-level atmospheric pressure, at altitudes up to 30,000 feet. This meant the R-3350 engines could produce approximately 1,800 horsepower continuously at 30,000 feet, compared to perhaps 600 horsepower for an unsupercharged engine. This 200% power increase transformed the B-29's high-altitude performance. Installation presented enormous challenges. Each engine required its own turbo-supercharger mounted in the aft section of the nacelle. Exhaust pipes, fabricated from stainless steel, channeled 1,600-degree gases from the engine to the turbine. These pipes had to flex to accommodate engine movement on its mounts while maintaining pressure ceiling. Leaks meant performance loss and fire risk. The compressed air outlet from the turbo-supercharger led to intercoolers mounted in the wing leading edge. These heat exchangers, using ram air for cooling, reduced compressed air temperature from over 400 degrees Fahrenheit to approximately 200 degrees before it entered the engine's mechanical supercharger. Cooler air is denser, containing more oxygen molecules per cubic inch, improving power output and reducing detonation risk. From the intercooler, ducting led to the engine's two-stage mechanical supercharger, driven from the engine crankshaft through gears. This combination turbo-supercharger plus mechanical supercharger gave the R-3350 extraordinary altitude performance. The turbo provided initial compression using free exhaust energy. The mechanical supercharger provided final compression for optimal manifold pressure. Together, they could maintain power at altitudes where enemy fighters struggled to reach. Flight engineer stations in the B-29 featured 4 turbo-supercharger control panels. Each panel included RPM gauge, exhaust gas temperature gauge, manifold pressure gauge, and wastegate position indicator. The flight engineer constantly adjusted wastegates to maintain optimal boost pressure as altitude, airspeed, and power requirements changed. This required skill developed through hundreds of hours of training. Automatic regulators assisted manual control. The pressure regulator automatically adjusted wastegate position to maintain preset manifold pressure. However, pilots and flight engineers often overrode automatic systems, manually adjusting for maximum efficiency. On long overwater missions where fuel conservation was critical, experienced flight engineers could extract additional range by precisely managing turbo operation. The fuel efficiency gains were remarkable. At 30,000 feet, cruising at 220 miles per hour, the B-29's 4 R-3350 engines consumed approximately 580 gallons per hour total. Without turbo-superchargers, achieving the same performance would have required flying at 15,000 feet, where fuel consumption would exceed 800 gallons per hour, reducing range by over 30%. The turbo-superchargers' efficiency made intercontinental bombing feasible. Range calculations demonstrated the turbo-superchargers' impact. The B-29 carried 8,188 gallons of fuel in wing and fuselage tanks. At optimal cruise settings, 30,000 feet, 220 miles per hour, the aircraft could fly approximately 3,200 miles with a 5,000-pound bomb load, sufficient for round-trip missions from the Marianas to Tokyo. Without turbo-superchargers, the same aircraft flying at lower altitude for equivalent performance would have range below 2,000 miles insufficient to reach Japan from any available base. The altitude advantage provided by turbo-superchargers had defensive implications beyond simple range extension. Japanese fighters in 1944 to 1945, primarily Nakajima Ki, 84, Frank, Kawasaki Ki, 61, Tony, and Mitsubishi A6M0 variants, had service ceilings between 35,000 and 38,000 feet theoretically. However, combat performance at these altitudes was marginal. Climb rates decreased dramatically above 25,000 feet. Maneuverability suffered. Armament effectiveness degraded. B-29 seconds. Cruising at 30,000 to 32,000 feet, operated at the edge of Japanese fighter capability. Interception required fighters to climb to operational altitude often 20 to 30 minutes, giving ample warning. At altitude, Japanese fighters struggled to maintain formation, experienced oxygen system problems, and had limited time before fuel exhaustion forced descent. The B-29's turbo-supercharged engines, by contrast, operated comfortably at 30,000 feet for hours. Anti-aircraft fire effectiveness decreased exponentially with altitude. Japanese Type 88 75mm and Type 99 88mm anti-aircraft guns had maximum effective ceilings around 28,000 feet. At 30,000 feet, shell bursts were infrequent and inaccurate. At 32,000 feet, achievable by the B-29 with reduced bomb-load anti-aircraft fire was virtually ineffective. The turbo-supercharger's altitude capability placed B-29 seconds above most Japanese defenses. The first B-29 combat mission from bases in India and China, on June 5, 1944, targeted Bangkok railway shops. The mission demonstrated both the aircraft's remarkable capabilities and the challenges of operating turbocharged engines in combat. Of 98 B-29 seconds dispatched, 77 attacked the target from altitudes between 17,000 and 27,000 feet. 5 aircraft were lost, but only 1 to enemy action. The others suffered mechanical failures, primarily engine problems. The R-3350 engine proved troublesome in early operations. Cylinder head temperatures exceeded limits, causing valve failures. Connecting rods broke. Most critically, engines caught fire during high-power operations. Investigation revealed multiple problems: inadequate cooling, improper engine break-in procedures, substandard magnesium alloy in engine components, and incorrect turbo-supercharger operation by inexperienced flight engineers. Modifications came rapidly. Improved cylinder baffling enhanced cooling, engine break-in procedures were revised, requiring 50 hours of careful operation before combat missions. Magnesium alloy specifications were changed. Most importantly, flight engineer training was expanded. By September 1944, when XXI Bomber Command began operations from the Marianas, turbo-supercharger-related problems had decreased significantly. The November 24, 1944 mission to Tokyo 111 B-29 seconds dispatched. 88 reaching the target validated the turbo-supercharger's strategic importance. The 3,000-mile round trip from Saipan represented the longest bomber mission of the war to that date. Flying at altitudes between 27,000 and 33,000 feet, the B-29 seconds encountered minimal fighter opposition. Japanese fighters reached operational altitude but couldn't sustain attacks. Anti-aircraft fire burst thousands of feet below the bomber stream. Mission reports documented turbo-supercharger performance. Aircraft 42-24621, piloted by Captain Robert Fitzgerald, maintained 30,000 feet for 7 hours, consuming 4,890 gallons of fuel for the outbound leg. Without turbo-superchargers, achieving equivalent performance would have required lower altitude flight, increasing fuel consumption to approximately 6,500 gallons more than the aircraft's total capacity. The turbo-superchargers made the mission possible. Flight Engineer Technical Sergeant James O'Brien of the 498th Bombardment Group documented typical turbo-supercharger management during a January 1945 mission to Nagoya. During climb to bombing altitude, O'Brien gradually closed wastegates as altitude increased, maintaining 46 inches manifold pressure. At 30,000 feet cruise, wastegates were 60% closed, turbo-superchargers spinning at 21,000 revolutions per minute, exhaust gas temperatures at 1,550 degrees Fahrenheit. Over the target, when pilots advanced throttles for evasive maneuvers, O'Brien carefully adjusted wastegates to prevent overboost while maintaining maximum power. The constant adjustments required undivided attention. Combat damage testing revealed turbo-supercharger vulnerabilities and remarkable resilience. Aircraft 42-65281, hit by 20mm cannon fire during a February 1945 mission, suffered exhaust ducting damage to the No. 3 engine's turbo-supercharger. The damaged ducting leaked exhaust gases, reducing turbo efficiency by approximately 40%. However, the engine continued producing adequate power at 28,000 feet for the return to Saipan, a 1,500-mile flight. The redundancy of 4 independent turbo-supercharger systems meant single failures rarely caused mission abortion. The most dramatic demonstration of turbo-supercharger capability came during missions to the Japanese home islands from Iwo Jima after its capture in March 1945. From Iwo Jima, B-29 seconds could reach any target in Japan with fighter escort, but the 1,500-mile round trip to Tokyo still required careful fuel management and optimal altitude performance. Turbo-superchargers enabled these missions with sufficient fuel reserves for combat maneuvering and emergencies. Maintenance statistics revealed the system's reliability, improving throughout 1945. In January 1945, turbo-supercharger failures averaged 0.8 per 1,000 engine hours. By May 1945, this decreased to 0.3 per 1,000 hours. Common failures included turbine wheel bearing failures, wastegate actuator malfunctions, and ducting cracks. Field maintenance crews developed rapid replacement procedures, swapping entire turbo-supercharger assemblies in under 4 hours. The efficiency advantages became quantifiable. Analysis of 500 B-29 missions from November 1944 through May 1945 showed average fuel consumption of 0.45 pounds per horsepower per hour at cruise settings, remarkably efficient for 1,940 seconds technology. Equivalent performance without turbo-superchargers would have required fuel consumption exceeding 0.65 pounds per horsepower per hour. This 44% efficiency improvement translated directly to range extension of approximately 1,200 miles. The difference between being able to reach Japanese targets and being unable to conduct strategic bombing. Japanese intelligence services recognized the B-29's altitude capabilities immediately after the first raids. Interrogation reports of American aircrews shot down or captured revealed disturbing information. These bombers operated comfortably at altitudes where Japanese fighters struggled, flew missions of unprecedented distance, and would inevitably increase in numbers as American production ramped up. Colonel Minoru Genda, architect of the Pearl Harbor attack and one of Japan's most brilliant air tacticians, analyzed B-29 performance in late 1944. His report to Imperial General Headquarters was blunt. The enemy's B-29 aircraft possess altitude and range capabilities that render our defensive systems inadequate. Their ability to maintain high speed at 30,000 feet suggests propulsion systems far superior to our own. Our interceptors can reach these altitudes only with difficulty and cannot sustain combat. Without technological advances we cannot match, the enemy will systematically destroy our industrial capacity. Japanese technical intelligence obtained a partially intact B-29 when aircraft 42 to 6,256 crashed off the coast of Kyushu on November 29, 1944. Recovery efforts retrieved the tail section, wings, and critically one relatively intact R-3350 engine with its turbo-supercharger. Japanese engineers transported the wreckage to Mitsubishi's research facility in Nagoya for detailed examination. The analysis report, captured after the war, documented Japanese engineers' findings. The enemy turbo-supercharger represents extraordinary engineering. Materials analysis shows turbine wheel composition we cannot replicate. Bearing systems exceed our manufacturing tolerances. The integration of exhaust energy recovery demonstrates fundamental advantages in thermodynamic understanding. Without similar systems, our aircraft cannot compete at high altitude. More tellingly, the report concluded, development of equivalent turbo-supercharger technology would require minimum 5 years and manufacturing capabilities we do not possess. Recommend acceptance that enemy possesses insurmountable technical superiority in this domain. This admission, from one of Japan's premier aircraft manufacturers, acknowledged the impossibility of matching American turbo-supercharger technology. Japanese attempts to develop high-altitude interceptors demonstrated their desperation. The Mitsubishi Ki-83 experimental fighter, designed for high-altitude performance, wouldn't fly until November 1944 and never entered production. The Nakajima Kicker, Japan's jet aircraft program, remained experimental. None of these programs could be developed and fielded in time to matter. American turbo-supercharger technology had rendered Japanese air defenses obsolete before they could adapt. The psychological impact on Japanese military leadership was profound. Prior to B-29 operations, military planners assured Emperor Hirohito that Japan's home islands remained invulnerable to strategic bombing. The appearance of B-29 seconds over Tokyo, in November 1944, flying from bases 1,500 miles distant, at altitudes Japanese fighters barely reached, shattered this illusion. War Minister Hajime Sugiyama's December 1944 briefing to the Emperor admitted, "The enemy possesses the capability to strike our homeland at will. Our defenses cannot prevent this." The industrial implications were devastating. B-29 raids targeted Japan's aircraft industry systematically. The Musashino engine factory, Nakajima's primary facility, was bombed repeatedly from November 1944 onward. The Mitsubishi aircraft works in Nagoya suffered similar treatment. By April 1945, Japanese aircraft production had fallen 50% from peak levels, not primarily from physical destruction, but from systematic disruption of component manufacturing and assembly. Emperor Hirohito's decision to accept surrender terms after Hiroshima and Nagasaki reflected recognition that continued resistance was futile. The atomic bombs demonstrated American willingness to use unprecedented destructive force, but the B-29 seconds that delivered those weapons represented a deeper truth. America possessed technological capabilities Japan could never match. The turbo-superchargers that enabled those 3,000-mile missions were merely one example of pervasive American engineering superiority. The strategic bombing campaign against Japan from November 1944 through August 1945 provides quantifiable evidence of turbo-superchargers' impact. Statistical analysis reveals how this single technology multiplied American air power effectiveness. The 313th Bombardment Wing, operating from Tinian, flew 1,047 sorties from January through March 1945. Average mission length, 2,000, 850 miles. Average altitude, 29,400 feet. Total bomb tonnage delivered, 8,470 tons. Without turbo-superchargers enabling high-altitude flight at extended range, these missions would have required bases 1,000 miles closer to targets bases that didn't exist. The efficiency metrics are revealing. At 30,000 feet, cruising altitude with turbo-superchargers maintaining manifold pressure, B-29 seconds achieved approximately 1.83 miles per gallon with 5,000-pound bomb loads. At 15,000 feet, without turbo-superchargers necessary to maintain equivalent airspeed, fuel consumption increased to approximately 1.26 miles per gallon. This 45% efficiency penalty meant missions requiring 4,500 gallons with turbo-superchargers would require 6,500 gallons without them, exceeding the B-29's 8,188 gallon capacity when return fuel was included. Combat loss rates validated altitude advantages. B-29 seconds flying above 28,000 feet experienced loss rates of 1.3% per mission. Those flying below 25,000 feet, where turbo-supercharger problems sometimes forced them, experienced 3.8% losses. The altitude protection provided by properly functioning turbo-superchargers nearly tripled survival rates. Japanese fighter interception effectiveness correlated directly with B-29 altitude. At altitudes above 30,000 feet, Japanese fighters achieved kill rates of 0.4% of bombers attacked. At altitudes below 25,000 feet, kill rates increased to 2.1%. The mathematical reality was stark. Operating above 30,000 feet, enabled by turbo-superchargers, reduced fighter threat by a factor of 5. Production statistics tell the industrial story. From 1943 through 1945, General Electric manufactured over 67,000 turbo-supercharger units across all models. The B-11 units for B-29 seconds totaled approximately 22,000, enough to equip 5,500 bombers plus spares. Japanese industry produced no equivalent systems. This disparity represented not just technical gap, but comprehensive industrial superiority. The cost-effectiveness calculation reveals strategic wisdom. Each B-29 cost approximately $640,000 in 1945 dollars. The 4 turbo-superchargers added roughly $40,000 to unit cost, a 6.25% premium. Those turbo-superchargers extended range by approximately 1,200 miles and increased altitude capability by 8,000 feet. Alternative approaches, building bases closer to targets or developing higher altitude engines, would have cost billions and taken years. The turbo-supercharger investment was extraordinarily cost-effective. The final accounting came in August 1945. B-29 seconds from the 509th Composite Group delivered atomic weapons to Hiroshima and Nagasaki from Tinian, round-trip distances of 3,120 and 3,200 miles respectively. These missions required flight at altitudes exceeding 30,000 feet to avoid the nuclear blast effects. Without turbo-superchargers, neither mission would have been possible from available bases. The technology that seemed merely incremental in 1940 enabled the war-ending strikes 5 years later. The story of how turbo-superchargers extended B-29 range by 2,000 miles transcends technical achievement. It demonstrates how sustained investment in fundamental engineering capabilities creates decisive military advantages that no amount of courage or tactical brilliance can overcome. The development timeline was long, from Sanford Moss's 1,918 demonstrations to the B-29's 1,944 combat debut, required 26 years. This extended development reflects the complexity of high-temperature, high-speed rotating machinery and the challenges of integrating such systems into operational aircraft. Nations unable or unwilling to sustain such long-term technical programs found themselves at decisive disadvantage when war came. The industrial dimension was equally critical. Turbo-superchargers required precision manufacturing, specialized materials, and complex quality control. General Electric's Lynn facility employed over 12,000 workers by 1944, producing 2,500 turbo-supercharger units monthly. This mass production of sophisticated devices reflected American industrial capabilities that Japan and Germany couldn't match despite their technical sophistication in some domains. The systems integration lesson was perhaps most important. Turbo-superchargers alone didn't make the B-29 revolutionary. They were one component in an integrated system that included pressurized crew compartments, remote-controlled defensive armament, advanced fire control systems, and sophisticated navigation equipment. American engineers excelled at integrating complex technologies into reliable, operable systems. This systems engineering capability proved as important as individual component excellence. Post-war analysis by both American and Japanese engineers concluded that turbo-superchargers represented a pivotal technology. Japanese studies estimated that equivalent turbo-supercharger capability would have extended their bomber ranges by 60% and increased altitude capabilities by 7,000 feet. Their inability to develop systems limited their strategic bombing capabilities throughout the war. The broader lesson resonates beyond World War II. Victory in modern warfare increasingly depends on technological sophistication applied through superior engineering and manufacturing. The nation that consistently develops, produces, and fields superior technology at scale possesses overwhelming advantages. The turbo-supercharger that enabled B-29 seconds to fly 2,000 miles further represented precisely this kind of advantage, incremental in concept, revolutionary in application, and ultimately decisive in outcome. When Major Robert Morgan's B-29 touched down at Isley Field on Saipan after that November 24, 1944 mission to Tokyo, Technical Sergeant Henry Carlson logged the turbo-supercharger performance data in his engineer's report. 15 hours and 18 minutes flight time, 4 turbo-superchargers operating within specifications throughout. Manifold pressure maintained at 46 inches at 30,000 feet. Exhaust gas temperatures normal. Fuel consumption as predicted. The numbers seemed cold, mere data points in a technical report, but behind those dry statistics lay a revelation about the true engine of victory in the Pacific War. They were not simply evidence of mechanical reliability or production efficiency. They were testimony to the fusion of scientific insight, industrial mastery, and disciplined execution that characterized American engineering at its wartime peak. The 4 turbo-superchargers that powered each Boeing B-29 Superfortress were not abstract innovations. They were tangible expressions of a national philosophy. That ingenuity, when harnessed to industrial capacity and logistical foresight, could overcome geography, weather, and even the limits of physics. Each of those turbo-superchargers spun at 25,000 revolutions per minute, enduring heat fierce enough to melt untreated steel, compressing air so thin that even human lungs would fail to sustain a flame. Yet they worked not for minutes, not for hours, but for the 15-hour duration of a mission that redefined the boundaries of air warfare. That reliability, multiplied across fleets of aircraft, allowed the U.S. Army Air Forces to strike Japan from bases thousands of miles away at altitudes beyond the effective reach of Japanese fighters and flak. It was a feat that Japanese planners had declared impossible, a fantasy of Western arrogance. But when the first B-29 seconds appeared over Kyushu and later over Tokyo, gleaming like silver needles in the stratosphere, that fantasy became an inescapable reality. The technical achievement of the turbo-supercharger went far beyond metallurgy and thermodynamics. It symbolized a shift in warfare itself, from the age of the warrior to the age of the engineer. In earlier wars, courage, discipline, and tactical brilliance could compensate for inferior equipment. In this one, those virtues could not overcome the laws of physics. The Japanese Zero, once the terror of the Pacific, had been designed for agility and dogfighting supremacy at low and medium altitudes. It was a weapon of pilots and instincts, not of machinery and mathematics. The B-29, by contrast, was a product of laboratories, drafting boards, and assembly lines. Its combat power did not come from pilot heroics, but from equations solved years earlier by metallurgists, aerodynamicists, and combustion specialists who would never see a battlefield. In that sense, the B-29's turbo-supercharger represented the triumph of intellect over intuition, of precision over passion. American engineers had achieved something extraordinary. They had turned raw heat, the chaotic energy of exhaust gases, into disciplined power. The supercharger's spinning turbines captured what would otherwise have been wasted energy and transformed it into lift, speed, and range. It was an almost poetic inversion of destruction into creation, waste into advantage. This was not just engineering, it was philosophy, expressed in metal. From a strategic perspective, the implications were revolutionary. The Pacific Ocean, once a vast defensive moat for Japan, became a mere obstacle to be crossed. Where Japan had relied on island fortresses and interior lines of communication, the United States relied on altitude and endurance. The turbo-supercharger extended not merely the aircraft's physical reach, but America's strategic imagination. For the first time in history, a nation could project decisive air power across entire oceans, bypassing the traditional constraints of geography. The Japanese High Command struggled to comprehend what they were witnessing. Intelligence officers reported aircraft arriving from distances previously thought unreachable. Engineers examined fragments of wrecked B-29 seconds and found materials and systems that seemed almost otherworldly: heat-resistant alloys, precision-machined turbines, and complex ducting far beyond Japan's own metallurgical capacity. Every investigation confirmed the same dreadful conclusion. Japan's war industry, ingenious as it had been in 1941, was now outpaced by an adversary whose factories functioned like research laboratories, whose workers operated with scientific precision, and whose logistics chains could sustain miracles as routine operations. The shock was not merely technological, it was existential. Japanese officers had built their doctrines on the assumption that courage could substitute for machinery, that the spirit of the warrior could overcome any mechanical shortcoming. But the B-29 erased that illusion. A bomber cruising at 30,000 feet, invisible to most interceptors, indifferent to flak, and capable of dropping 10 tons of bombs with radar-guided precision, could not be stopped by courage. It was an enemy born of equations and production quotas, of conveyor belts and blueprints. Against such an enemy, even the most fanatical resolve became irrelevant. This transformation in the nature of warfare was what made the B-29 and its turbo-supercharger so historically decisive. The aircraft was not simply a bomber, it was a flying demonstration of what industrialized science could achieve when mobilized for war. Its existence announced that the age of industrial-scale engineering had arrived in full force. Every successful mission was both a military strike and a statement of philosophy. That mastery of technology was now synonymous with mastery of destiny. Consider the broader arithmetic of the war. In military equations, range equates to reach, and altitude equates to survival. The B-29's turbo-supercharged engines provided both, allowing bombers to climb higher, fly farther, and return safely from missions that would have been suicidal for earlier aircraft. The result was a self-reinforcing cycle. Greater range meant new bases were unnecessary, reducing logistical vulnerability. Greater altitude meant fewer losses, preserving crews and aircraft for repeated missions. Over time, that reliability accumulated into strategic inevitability. The Japanese could replace pilots more easily than scientists, but America could replace machines more easily than men, and that was the decisive asymmetry. The B-29's performance was not an isolated miracle. It was the culmination of a national ecosystem of innovation. The turbo-supercharger had been refined through thousands of test hours by General Electric, a company whose engineers labored tirelessly to perfect turbine materials, airflow patterns, and cooling systems. Those same engineers worked hand in hand with the Army Air Forces, ensuring that design feedback from the field translated into production improvements. In that collaboration lay the essence of American strength, the seamless partnership between industry, science, and the military. Meanwhile, on the Japanese side, the limitations were painfully clear. Their own aircraft engines struggled to operate efficiently above 20,000 feet. Shortages of strategic metals, nickel, chromium, molybdenum crippled attempts to build comparable turbines. Wartime blockades strangled their access to the raw materials required for high-temperature alloys. Even where the Japanese possessed theoretical knowledge, they lacked the industrial infrastructure to translate it into mass production. In effect, Japan faced not just a technological gap but a civilizational one, a gulf between an industrial society and a militarized artisan economy. The thunder of 18 turbocharged cylinders echoing over Tokyo was therefore more than the sound of engines. It was the sound of inevitability. Each roar proclaimed that the outcome of the war had already been decided, not by generals or admirals, but by scientists, engineers, and machinists who had long since turned theory into hardware. The bombs that fell from those aircraft destroyed cities, but the greater destruction had already occurred. The annihilation of Japan's confidence in its ability to compete technologically. By 1945, the turbo-supercharger had become more than a mechanical component. It was an emblem of modern war's new reality, the idea that national survival depended on mastery of complex systems. The same principles that enabled B-29 seconds to fly above the clouds would later power jet engines, nuclear reactors, and space rockets. The war had proved that whoever controlled high energy and high altitude would control the future. When Japanese observers looked skyward and saw silver bombers tracing contrails across the blue, they were not merely witnessing an enemy attack. They were seeing the horizon of a new age. In that thin air, where oxygen was scarce but innovation abundant, the United States demonstrated the final convergence of science and strategy. The battle was no longer between pilots, but between engineers. And in that contest, Japan was not merely defeated, it was rendered obsolete. In the end, the story of the B-29's turbo-supercharger is a story about transformation. It shows how a seemingly small component, a turbine wheel spinning unseen inside an engine nacelle, could alter the course of nations. It reminds us that victory in modern war does not belong to those who fight hardest, but to those who think deepest and build best. When the first B-29 seconds flew unchallenged across the Pacific, they announced more than air superiority. They heralded a new order, one in which industrial intellect had become the ultimate weapon, and in that new order, Japan's fate was sealed long before the bombs fell. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.